Hello everyone. My name is Feng Wang. I come from Alibaba. Now I'm working at Alibaba real-time computing team, and my team has been working on Flink for nearly 3 years, since 2015. In recent Flink board conference, I have shared some topics about Flink runtime improvements for Flink streaming. Today, my talk is about the runtime improvements for Flink batch. Okay. First, I will give a brief introduction about Alibaba and how Flink runs in Alibaba. Then I will talk about the current Flink API stack and the problem of it. And I will give a new proposal for it, which is of advantage to make Flink as the unified computer engine for both streaming and batch. Next, I will share some runtime improvements dedicated for batch processing, which range from job schedule, job failover, the shuffle service, and the task execution. In the last, I will give our future plans. So first, let's begin with Flink in Alibaba. Alibaba's mission is to make it easier to do business anywhere, which aims to build the future infrastructure for commerce. Alibaba now not only provides the online trading system for numerous merchants and consumers globally, but also provides a cloud computing service for many middle and small-sized enterprises across the world. So now the data in Alibaba has been increasing tremendously in recent years. Now the total data size in Alibaba has reached EB level, and every day there are trading events happen in Alibaba. Petabytes of new data produced, and at the peak, there are hundreds of millions events happening in Alibaba per second. So facing such huge scale and fast-growing data in Alibaba, we must have a powerful data platform for both streaming and batch processing. So after a variety of study and research, finally we choose Flink as our core computing engine and build a unified computing platform on top of it. Okay. Let's see our Flink computing platform in Alibaba. In Alibaba, we have an internal Flink version, which is with a lot of improvements to make Flink can run reliably and efficiently for large-scale applications. And some of them have been contributed to a Flink community, such as Flip 6 architecture and incremental checkpoint, the credit-based flow control, and so on. To leverage the existing Hadoop cluster in Alibaba, all our Flink jobs are deployed on Yang with Flip 6 architecture, and all the states data are persistent on the HDFS cluster. And in Alibaba, most of the developers prefer to use SQL or table API to develop Flink jobs, because this high-level relational API is more convenient and efficient for developers to develop Flink jobs. To further facilitate the operation and development of Flink jobs, our team also developed a Flink development platform named Bayes, by which users could submit jobs, monitor jobs, debug jobs, and stop jobs with in a integrated web UI. Now, almost all the key data applications in Alibaba have run on top of our Flink computing platform, and such as search, recommendation, ads, security, business intelligence. Okay. Now let's see some important Flink metrics in Alibaba production. The first Flink production cluster was launched online in 2016 with just several hundreds of nodes, which is dedicated for search application. But with 2 years development, now the scale of the Flink cluster has increased to more than 10,000 nodes. In addition, the older the data size of the job state has reached PB level. Now, every day there are trillions of events has been processing on our Flink computing platform. And at peak, the TPS has been excess of 4,072 million events per second with sub-second latency. Okay. In addition to provide the internal Flink computing platform, we also began to provide the public Flink computing service through Alibaba Cloud, because we find that there are more and more enterprises with strong motivation to move their data application onto Flink. So we hope that we can our Flink cloud service could help them to reduce the cost and improve the efficiency during this procedure. Okay. Okay. Although Flink has been widely adopted in more and more companies, but most of them use Flink only as the streaming solution. But most of the time, users also have the requirement to process the data periodically in batch mode, as well as stream mode. So the users must develop a batch job again using other batch processing technology, such as Hadoop or Hive or Spark. So, but obviously, the business logic in stream mode and batch mode almost the same in most of the cases. So if Flink can provide powerful batch processing capacity as well as streaming, users may choose Flink as a unified solution. So, in recent half a year, our team began to put more emphasis on the Flink batch mode. Aims to make Flink could process large scale of batch data as well as streaming data in Alibaba. Now, in the rest of my talks, I will show some of the works for this goal. First, I will talk about the unified core API for Flink, which we think is the process of the unified processing. Okay. Now, first, let's look at the current Flink API stack. Now, the data stream and the data set are the two kinds of core API in Flink's API stack. The former is data stream is dedicated for streaming, and the data set API is dedicated for the batch. And there are unified high-level relational API built on top of them, named the table API or SQL. The biggest problem of this API stack is that the data stream and the data set APIs go through different code paths during the compiling procedure. For example, a data stream program will be translated to a set of transformations and then generates a string graph. Finally, they will be converted to a set of stream tasks in runtime for the execution. But a data set program will be translated to a batch plan, then be optimized, and finally be converted to a set of batch jobs for execution. So in a word, the Flink has not a formal unified core API. The other problem is that now the operations or the transformations in both data stream and data set is already with specific semantics. So the high-level table API, which built on top of them, will be restricted by them. Okay. So in order to solve this problem, we proposed a new Flink API stack shown as the picture. We can see we propose to add a new kind of DAG or DAG API as the unified core API for Flink, which is without any semantics. And other APIs such as the datastream, the set, or the table API with semantics are considered as high-level APIs. All of them will be built on top of the same core unified core API. Due to Flink is a streaming computing engine essentially, so we choose the stream graph as the base of the new DAG API. And we choose the stream operator as the base of the new unified operator. Also, the stream task as the unified runtime task. Okay. Furthermore, in order to meet the requirement from the batch processing, we also need to add some more features to the stream operators to make it adapt to the requirement from the batch processing. Okay. Now I will show how we modify the stream operator. Okay. Let's see a batch example. This is a classic hash join batch job. It is known to all that the hash join operator, the hash join operation has two stages. The first stage is the build stage, and the second stage is the probe stage. So in the first build stage, the hash join operator will read data from one side and build a hash map internally. Then it will read data from another side and look up the hash map build before to complete the hash join. So in this case, we can see that the hash join operator have the requirement to decide the read order. But unfortunately, currently the stream operator has no method to do this. So we need to add more methods to the stream operator to make it adapt to the batch processing. First, we add a method to let the stream operator to indicate which input side it should read in the firstly. The return value any represents both sides are okay. This is the behavior of the stream mode. Furthermore, we should also add an input and notification method to the stream operator. In this case, the hash join operator could use this notification method to complete the build stage, the first build stage, then switch to the second probe stage. For some complex batch job, they may need to switch between the input size back and forth. So we should also need to modify the process element methods, change the return type to make it could indicate which input side to read for the next processing. So with this modification, the new stream operator could handle all the requirements from batch processing. Okay. Okay. Next, I will talk about the runtime improvements for batch processing. Besides the API change, we also in order to make Flink batch job could run stably, reliably, and efficiently in Alibaba production for large-scale applications. We also made a lot of runtime improvements for it. Now I will share them divided into 4 parts. The first part is about job schedule, which could make the batch job scheduled more flexible. And the second part is about the job failover, which could make the batch job run reliably in Alibaba production. The third part is about the shuffle service, which could make Flink batch job use external shuffle service. The last part is about the task execution, okay, which could make the batch job run more efficiently. Let's begin with the job schedule. Now Flink, there are 2 kinds of the schedule mode in Flink. The first one is eager mode. And the second one is lazy from source mode. In the eager mode, all of the execution vertices will be scheduled after all the resources have been allocated. So it is the default schedule mode for stream mode. The latest, in the lazy from source mode, all the vertices should be scheduled from source to sink sequentially. So this is the default mode for the batch mode, for batch job. But both of them cannot perform efficiently enough to satisfy the requirement from the complex batch job. Let's see the hash join batch example again. Okay, I have illustrated how the hash join operation works. The hash join operation will read data from the build side firstly, and don't read the data from the prop side until the build stage finish, like this. So we can, in this job graph, we can infer that we should schedule the build side vertex and the hash join operator firstly. Then after the build stage finish, we can the prop side vertex should only be could be scheduled. Even if the prop side vertices are scheduled early, they can be still blocked. So this also could result in a lot of waste of resources. Okay, in order to meet the flexible schedule requirement for the batch job, we proposed a new pluggable job schedule framework for Flink, which could make Flink schedule flexible enough to meet all the various kinds of the requirement from batch processing. This is our design. In this design, we bring up with new concepts. The first one is DAG Manager, and second one is Task Scheduler. The DAG Manager is a plugin in which user or developer could decide when to schedule which vertices, driven by the DAG event, such as execution vertex state changed, or the result partition becomes consumable. And the task scheduler is a new interface provided by Runtime framework, by which users could trigger the task scheduling for a specific execution vertex. Okay, this is the interface of the DAG Manager plugin. There are several methods in this interface. The first one is the open method. This method will be called after this plugin was created. So under the task schedule and the job graph will be passed into it. The close method will be called after the plugin was stopped. So we can do some cleanup works in this method. Now the first critical method is in this interface is the onScheduling started method. This method will be scheduled when the scheduling is started. We can schedule all the vertex in this method unstarted to implement the eager mode. Then the unresolved partition consumable method will be called when any result partition becomes consumable. So in this method, we can schedule all the downstream tasks when the upstream tasks become consumable to implement the lazy from source mode. And the on-execution vertex state changed method will be called when there are any execution vertex state was changed. So in the hash join example, we can schedule the prop side vertices after the build side vertex finish. So, okay. So this is our new design for the DAG Manager plugin. Okay. Next, we'll talk about some of the works about the job failover. which could improve the reliability and stability for the Flink batch job. Okay. Now there are two kinds of failover in Flink. The first one is task failover or TM failover, and the other one is the GM failover. Now, Flink has for the task failover or TM failover, Flink has provided two kinds of failover strategy. The first one is restart all strategy, and the other one is region-based strategy. But now the Flink has only provided one failover strategy for the GM job manager, restart all strategy. It is easy to know that the restart all strategy will restart all the tasks after the GM was restarted. So for streaming mode, all the tasks could recover from the latest checkpoint after the GM was restarted. So to some extent, the result is acceptable. But for the batch job, all the tasks had to run from scratch after the GM was started. So this is a disaster for the batch job user. Even the probability of GM failure is not high, but the consequence is very serious. So in order to solve the failure problem, we have added a new failure strategy to the GM failure, which could take over all the running tasks and finish tasks after the GM was restarted. So users could in this design, this is our design for this strategy, failure strategy, and I will show how it works. First, we introduced a new component named operation log, which is in charge of to store the operations of the execution graph. When the GM was restarted, the execution graph could replay the operation from this log to recover its internal state. And of course, accordingly, it will generate a series of DAG events. The DAG manager could replay this DAG event to recover its internal state and generate a schedule plan. After the GM recovered its internal state from the operation log, it will reconcile with the task managers. From the task manager side, the task manager could detect the failure of the job manager, and they will try to reconnect it to the new job manager. After the TM connected to the new job manager, it will send its task report to the job manager. Then, if the job manager finds there are some conflicts between the execution graph and the task report, the corresponding execution vertices will be marked as failed. After the reconciliation finished, the schedule plan generated from the task manager will be executed, and of course the running task and the finished task will be skipped. Finally, if there are some failed tasks inferred by the reconciliation, it will be handled by the task failure strategy. After all this work's done, the GM will be recovered completely without any interference to the running and the finished tasks. Okay. Next, I will talk about the shuffle service. Now the first I will introduce two kinds of the shuffle mode. In Flink, there are two kinds of shuffle mode. The first one is pipeline shuffle, and the second one is the blocking shuffle. So the pipeline just as their names imply, the pipeline shuffle will transfer data from upstream task to downstream task as long as the upstream task emit first buffer, data buffer, and only through memory and the network. So it is suitable for both streaming and batch. The blocking shuffle is quite different from the pipeline shuffle. It will transfer the data from upstream task to downstream task after the upstream task finish. And the immediate result may be spilled to the disk if the memory is not enough. So it's dedicated for batch job. So for the pipeline shuffle, if there are one task failure, all the tasks connected with it will be restarted. All of them will be restarted. But for the blocking shuffle, only in the field task will be restarted. So the blocking shuffle can bring better fault tolerance for the batch jobs. But there is also a restriction in the blocking shuffle that even there are no running tasks in a task manager, the task manager cannot be released because it should serve the shuffle service for the finished tasks ever running in it. The root cause of this problem is that the shuffle service is coupled with the task manager now, but the life cycle of the two different components is not the same. Okay. So to solve this problem, we proposed a pluggable shuffle service interface, which could decouple the shuffle service with the task manager, and the developer could use this pluggable interface to implement more kinds of external shuffle services, as well as the internal shuffle service. In this pluggable interface, we bring up a new concept, new interface named Shuffle Manager, which could create many different kinds of result partition. The result partition is responsible for the storage of the immediate result data, which corresponds to the specified shuffle service. Now we have implemented two kinds of shuffle service. The first one is internal TM shuffle service, located in TM, which do the same thing as the current Flink shuffle. And another one is the external Yang shuffle service. Okay. This is the architecture of the external Yang shuffle service. From this picture, you can see that the Yang shuffle service is deployed in Yang Node Manager as a Yang plugin. And there's only one shuffle service on one physical node. So it is possible for it to manage the network I/O and the disk I/O globally for all the Flink tasks running on that node, but in different task managers. So this design could get the best performance. Another advantage of this architecture is that the Yang shuffle service could make the task manager become shuffle-free and run more flexibly and efficiently, which could result in more efficient resource utilizations. Now we have provided two storage policies for the result data in Yang shuffle service. The first one is the hash policy. And another one is the sort merge policy. For the hash policy, all the immediate result data will be spilled into different files divided by the result subpartition. This is the sort merge policy. In the sort merge policy, all the result data will be buffered in fixed memory segment firstly, then be flashed to the disk as a sorted file repeatedly when the memory is full. So finally, all the sorted file on disk will be merged into a global single one file, also with the index. So it is obviously the hash policy is suited for the middle and small sized batch job. but not large-scale batch job, because there will be too many small files in large-scale batch jobs, which is harmful to the performance. And the sort merge policy is dedicated for the large-scale batch job, because all the result data will be merged into a single global file without any fragments. Okay. In the last part, I will talk about feature improvements about the task execution. Okay, this feature improvement is about the operator chain. Now in Flink, if some operators with same parallelism and the shuffle mode between them is forward and pipeline, they can be changed together and executed in the same process. And obviously, there are two benefits of the operator chain feature. The first one is that it could eliminate the network I/O between the different operators, and another one is it could reduce the cost of serialization and the deserialization of the records between the operators. But there's also a constraint of this chain feature, that all the operators in the operator chain should have only one input, except the head operator. So this input constraint will limit the effect of this chain feature, especially for the complex batch job. So if we can get rid of this one input constraint from this chain feature, we could get more performance gain from this feature. Okay, this is our new design for the operator chain. Of course, without any input constraint. Consequently, there will be multiple head operators rather than one in this design. So the main process thread should switch among all the head operators and choose the ones which have the data to consume currently. So the biggest challenge for this new design is about the source function interface, because now the source function provides a run method in which the user code could read data from the storage and push data to the downstream repeatedly. So the main processing thread cannot jump out from this run method as long as enter into it and switch to other head operators to read the data. So to solve this problem, we proposed a new kind of source function interface, which replaces the run method with next method. So in other words, we use the pull mode pull mode instead of the push mode for the data injection in the source function. So after this using this new source function interface, the main processing thread could switch among all kinds of head operators freely. And the checkpoint barrier handler in this design could keep its original logic with little changes, so the checkpoint feature cannot be affected for stream mode. Okay. All of these runtime improvements has been adopted in our Alibaba production now. But I think this is only the beginning of making Flink as a unified computer engine for both streaming and batch. And we also have a lot of future plans in the future. Okay, the first plan is about deployment. Now there are now in Flip 6 architecture, the patrol mode and the session mode go different code paths. So we want to provide a new unified session mode for Flink in Flip 6 architecture, which is elastical, which could be elastic according to the resource requirement and the workload. The second one plan is about the job scheduling. Now, the job graph cannot be changed after it has been submitted, which is a limitation for both streaming and batch. Because sometimes in stream mode, a user sometimes want to online update the job graph without restart the job. And for batch mode, the SQL planner sometimes want to decide the next plan dynamically according to the result from the previous finished stage. So we plan to pay more attention to the dynamic update and hot update mechanism for the job graph. The third one is about network stack. In addition to further improve the performance of Yang shuffle service, we also want to explore more kinds of external shuffles, such as RDMA shuffle. The last one is about the checkpointing and the state backend. Now, the heap state backend perform very well in Flink, but the OM problem is hard to handle for normal users. So we plan to provide a new kind of heap-based state backend to solve this problem. And now the checkpoint can only work in stream mode. But cannot work in batch mode. So we also want to explore how to make checkpoint work in batch mode. In other words, we want to explore the new unified checkpoint for both streaming and batch. Okay, that's all of my today's talk. Thank you. Any question?
Thank you very much.
Thank you. Great talk. So I have a question about what you did in the job failover. Okay. So what I understood, you added like a report log or append log or something that was so it will like inform you after restarting the job manager where the batch task stopped. Is that correct?
I guess your question is about the job GM failover and the operation log.
Yeah.
Yes. Yes. We will this time we will store all the operations to the external graph. Store this event to the stop the operation to the X graph to the operation log. Then, if after the GM was restarted, firstly the external graph can read the operations from the operation log to recover its state, internal state. So it can recover the state before it was restarted, before the failure. Okay.
Hi, really good talk, thank you. Those are really interesting proposals, and I was just wondering, is this something that we can already try out, or do you plan to contribute it back to Flink community?
Yes, I think this all these features we want to contribute to Flink community in the near future. And some of them have been, we have opened some JIRAs for them, such as self-service, we have opened JIRA.
Well, maybe we have time for one more question.
It wasn't very clear to me why the external shuffling service is more efficient and more flexible. I didn't get that point. Can you elaborate?
Okay, the first question is why shuffle service, Yang shuffle is more efficient. Yes, okay. Because now there may be several task manager, multiple task manager right in one machine node, a physical node. So they can this task manager cannot manage the global coordinate, the I/O and the network I/O and the disk I/O. Centralized. So, but there's only one shuffle service in one node because it is located in Yang node manager. It can coordinate all the network I/O and disk I/O for this node. All the disk and the network will be managed by it, so it can get the best performance. Second one is why task manager could be more flexible. Because now the task manager have the role for shuffle service. Even there is no task running in it, the task manager cannot be released because it should serve the request from other tasks to fetch the data from the finished task ever running in it. So, in this dimension, it was a shuffle service, not a task manager. So it is not flexible. If we have an external shuffle service running in a node, the task manager can be released if there is no task in it.
All right.
Okay.
Thanks a lot again.
Okay. Thank you.